Good morning, everyone. It is my great pleasure to give a talk on my recent research at this scientific machine learning workshop. The main topic I'm going to talk about will be focused on optimal experimental design for complex uncertain systems and especially systems that are described based on coupled ordinary differential equations. So this is the outline of my talk. I'm going to start with a brief introduction about the concept of MOCU, the mean objective cost of uncertainty, and how it can be used for objective uncertainty quantification. After that, based on using the concept of MOCU, I'll explain how we can use it for prioritizing effective experiments and basically for designing optimal experiments based on the expectation of the payoff for performing a given experiment. I'll introduce an example based on the so-called Kuramoto model, which is an interconnected oscillator model. It's a simple mathematical model based on differential equations, but then surprisingly versatile. And so many of you may have already heard about this model, and then show how OED can be performed for a Kuramoto model with uncertain parameters. So let's start with the objective-based uncertainty quantification using the mean objective cost of uncertainty. So in many cases, the reason why we care about scientific machine learning is because we are interested in scientific discoveries, solving problems regarding complex scientific systems, and so on. And we already know that many real-world systems, especially scientific systems, physical, chemical, material systems, are extremely complex, and it is practically impossible to identify the system or model them perfectly. We always talk about big data. However, if we think about the complexity of such systems, the data may be actually not that big compared to the complexity. So even though data is always useful, it may still leave behind substantial uncertainty regarding the system. So let's think about the problem of inferring a biological network. We can start with data, like gene expression data, and we may want to learn about the regulatory relationship between the genes. We could also use prior knowledge, basically some partial regulatory knowledge about how some genes regulate other genes, right? But at the end, what we end up with is not the exact true regulatory network, but an uncertainty class that comprises of potential networks that are consistent with the data and the prior knowledge that we have. So knowing that there will be always substantial uncertainty, even if we try our best based on the available knowledge and data, what might be a good way to proceed? Instead of aiming at accurate model identification, it may be actually much more reliable and robust to take a Bayesian approach to think about the uncertainty in the model and then develop learning, inference, and optimization methods that take this uncertainty into consideration. Then one practical question would be, knowing that there will be always substantial uncertainty in our complex system or a model reflecting the complex system of interest, how can we quantify how much uncertainty we have in the model or in the given model uncertainty class? From an engineering or practical perspective, we don't actually care about the model uncertainty itself, but how that uncertainty in the model at hand will impact the operations that we want to perform. For example, we may be interested in accurate prediction of certain trends. We may be interested in robust control of that system reflected by this mathematical but uncertain model, right? So what we care about is how does this uncertainty in my model affect the operation that I want to perform and the goal that I would like to achieve. So this means that when quantifying the uncertainty, it may make sense to do that based on how that uncertainty impacts our operational goal. So that's the underlying concept of mean objective cost of uncertainty. So let's take a look. The second term here shows CSI is the cost for applying psi, which is the operator. And both of them depend on theta, where theta is the parameter that defines the mathematical model of the system. So if we have full knowledge of the system, theta, then what would we do? Well, we would design the operator psi theta that is optimal for the theta. However, we cannot do that because we cannot model the true system perfectly, right? For that reason, instead of using the operator that is optimal for a specific system, we may have to rely on using a robust operator. So you can see that there the dependency on data is gone, right? We call it psi star. What is it? It's basically a robust operator that is designed to retain good performance, whatever true model is. So we want to design the best robust operator that maintains good performance across all possible models in the uncertainty model class. So basically, what does this MOKU, this definition, capture? Basically, it shows us the expected increase of the operational cost. And where does it stem from? Basically, from the fact that because there is uncertainty in the model, we cannot use the optimal operator that is optimal for that specific true model, which is not known, but we have to rely on robust operator that performs well, whatever the true model is. So there is an expected increase of this operational cost, and that is captured by MOKU. And well, you may see it, if you are familiar with the term metric regret, you can see that this is actually the minimum expected regret. So how can we use MOKU for doing optimal experimental design? We started with constructing the uncertainty class or the uncertainty model class, and we wanted to quantify how much uncertainty we have. And when doing that, we wanted to think about the impact of the uncertainty on the operational objective that we want to achieve. Now, once we have MOKU, we can ask the following question. Suppose we perform a given experiment, then what is the expected return on investment? If we perform that experiment, how much would it reduce the MOKU, right? So given an experimental design space, what we can do is try to compute the expected MOKU that still remains after performing a specific experiment. And then based on that, why don't we choose the experiment that is expected to reduce this uncertainty or the impact of remaining uncertainty as much as possible? So we can go through this loop as many times as possible or as much as our experiment budget allows. Now, in order to better understand this concept of optimal experimental design using MOKU, let's think about a specific problem, basically the Kuramoto model. So what is a Kuramoto model? It's a Kuramoto model consists of a set of n interacting oscillators, and those interactions are described based on ordinary differential equations. You can see that theta I, which is the angle of the ith oscillator, depends on a couple of terms. The first one is the natural frequency that is inherent for that given oscillator I. And then you can see the interaction terms between the jth oscillator and the ith oscillator. Basically, if the angles, if the gap between these angles increase, and if Aij is positive, the interaction strength, then the oscillators tend to pull each other so that they can bring theta j and theta I closer to each other. Of course, Aij may be negative in that case. If this this means that they will be pushing each other. So this is an illustration of a 5 oscillator Kuramoto model, and as it shows, it doesn't have to be fully connected. You have a Kuramoto in this form, and before we move on and think about uncertainty, I'll show you some interesting. Oh yeah, I hope you can see the video. So this is a 2 oscillator model. As you can see, even though they have different original natural frequencies, sooner or later they get synchronized, right? Now, I'll show you another example where the oscillators never get.
Hey, I have a question. Is this supposed to be an animation? Because I don't see, I just see a static slide.
Oh, really? You don't see anything? Okay. It is actually an animation.
I see it.
Yeah.
Oh, you cannot see the animation?
I'm seeing it on my side. I can see it. I don't know.
Okay. So I'll try to share the PowerPoint for those who cannot see it. So in this example, you can see that the oscillators do not catch up with each other. It is because the gap between the inherent frequencies are too big and the interaction strength is too small for them to catch up each other. This is another example where you can see that, there are quite a few oscillators and they get synchronized very, very quickly due to their interaction. Okay, now suppose we have a Kuramoto model of n oscillators, and we are assuming that the natural frequencies of those n oscillators are known. However, the interaction strength, Aij, between the oscillators are uncertain. And such a scenario happens actually pretty often because individual parts or components of a system may be tested very accurately. However, the interactions may be very, very complex and very difficult to identify accurately. So this is an interesting use case of, how do we analyze and design experiments for a complex uncertain system with where the interaction, how they interact is not clear. So based on this assumption, well, we can think about uncertainty class of potential Kuramoto models. Now, what is our objective? Based on this uncertain Kuramoto model, suppose you want to apply external control such that you can induce frequency synchronization through control, okay? Of course, we may know how to achieve this with minimal control cost if we knew what this true Kuramoto model is. However, this is impossible in this case because the interaction strengths are not known. So in the presence of uncertainty, how can we apply the optimal control? And then there are two important things. We need to achieve global synchronization, and at the same time, we want to minimize the cost of control despite the uncertainty. Based on this objective, now let's think about, well, if we had the luxury of performing additional experiments, based on whose outcome we could reduce the uncertainty in the Kuramoto model, what is the best experiment to perform? So this is the optimal experimental design problem. For simplicity, we think about an experimental design space that mainly consists of pairwise synchronization experiments. So what is it? Basically, we take a pair of Kuramoto model oscillators from the entire system. We simply let them run without any external control and just observe, will they synchronize if there is no external control, or will they never get synchronized? Okay, very simple experiment. So based on this experimental outcome, well, we can guess that we'll have further knowledge about how the interaction strength between those two chosen oscillators will look like. So, and that'll lead to a reduction in the overall model uncertainty. How many possible pairwise experiments do we have? If we have n oscillators, well, we have n choose 2. So n times n minus 1 divided by 2 possible pairwise experiments. So now, the main question is, how do we prioritize potential experiments? Okay, so for that purpose, we use this mathematical theorem. So one of the points in my talk is when we know something about this underlying system, like this theorem, then we can make use of it to design experiments. Okay, so what does it say? Basically, it says that if there are two oscillators in a Kuramoto model, they get synchronized if and only if, well, their natural frequency is within a range k, and k exactly depends on the pairwise interaction strength. So based on that, once we observe the result of synchronization of a pair of oscillators, we either can update the upper bound, like shown here, or we can update the lower bound. Okay, that reduces the uncertainty. Hence also reduces the MOKU. Now, the most important question is, from the experimental space that contains all possible experiments, which experiment is expected to be most useful, right? And for that one, we estimate the remaining expected MOKU. So basically, what is it? Suppose we want to choose the experiment that runs for the pair I and j, and then Bij is the result. Do they get synchronized or not synchronized? Based on that, we update the model uncertainty class and then estimate the MOKU, okay? Of course, before performing the experiment, we don't know the result. That's why we need to compute this expectation. And we can compute the expected MOKU that still remains after performing the experiment. So let me show how well it works. So what is the best thing that you can do if we didn't have this framework? Well, maybe you could just randomly pick your experiment, right? And see how much it reduces the model uncertainty. And as a result, how much it improves the control performance or minimize the control cost. That's what's shown here in the blue line. Or if you are if you want to use information theory, you could take a look at the entropy of the uncertain parameters and then try to reduce the entropy of the uncertain parameter that has the largest entropy, right? That's what's shown here in the green line. Of course, sometimes that'll work well, and sometimes it's not going to work. Why? Because entropy is agnostic of how you want to use the model. What is the objective that you want to achieve based on this, model, right? So as you can see in this example, based on a 5 oscillator Kuramoto model, the red line which shows that we are picking the experiment based on which one has the smallest expected remaining MOKU. Okay, as you can see, the first 1, 2, and 3 experiments quickly reduce the uncertainty, right? So MOKU is always very, very effective in capturing the experiment that is expected to reduce the uncertainty most effectively. And this example conveys that, conveys that advantage. This is another example based on 9 oscillator model. So we have 9 choose 2, so 36 different experiments. And from that, we want to pick the experiment that is expected to be most effective. As you can see, the MOKU-based experiment shown in red quickly picks the experiment that can most effectively reduce the overall uncertainty of the model and thereby improve the control performance. In this case, the random approach and also the entropy-based approach wasn't too bad, but then the point is, well, we can always guarantee that on an average sense, MOKU will be able to give you a prediction of the experiment that is predicted to be most effective. Now, we have a complex uncertain system described by differential equations. In this case, ordinary differential equations. And well, you may also have a system that is described by uncertain PDEs, right? And you may want to design, well, experiments that are expected to be most effective in reducing the uncertainty. What is the role of machine learning? Well, there are many ways that machine learning schemes can be used for accelerating the overall OED process. This shows one example where we use machine learning for deciding and predicting the robust operator, basically the external controller that is added to the uncertain Kuramoto model to guarantee global synchronization of all the oscillators despite the uncertainty in their interaction strength. You can see that, well, the Monte Carlo sampling-based method, which, well, achieves very good result, but very, very costly. And here's the red one, which shows the performance based on the machine learning-based acceleration method, right? You can see that they virtually have the same performance in terms of the effectiveness of the predicted experiments. And as you can see, they are always much better on average based on other methods compared to, for example, the entropy-based method shown in green or the random method, okay? And well, as you can expect, when you randomly select the experiment, on average, it's going to only linearly decrease the uncertainty. And that's what you are seeing here based on 100 randomized experiments.
Yep. Byung-Jun,
However,
I'm sorry
yes.
to interrupt. We are already 5 minutes past.
Oh, okay. Give me just 1 minute. Let me just conclude my talk. Okay. So, and as you can see, the speed can be accelerated by 2 orders of magnitude. And this is another example based on a larger model that consists of 7 oscillators, but then the trends are the same. So, concluding remark. We can do objective-based uncertainty quantification using MOKU, and that can be used for designing optimal experiments. And the Kuramoto model OED problem that I just showed you shows how the advantages of such method. There are many ways we could use machine learning for building surrogates for the model, or solving the differential equations, or accelerating decision making, and ultimately optimal experimental design. And many of the talks and many of the methodologies that the other speakers will talk about, I'm sure can be plugged in and used together for accelerating OED, reducing uncertainty in models that we care about through machine learning. And that concludes my talk. Thank you very much.
Thank you, Byung-Jun. That was very interesting. I think that this has a very interesting connections with scientific machine learning. So, any questions from the audience? I have a question. So, you mentioned, of course, you mentioned gene regulatory networks, and obviously, there's a lot of potential here for scientific machine learning. Of course, you can describe a gene network by a system of ODs, and I believe that you have studied this problem. Am I right? How to apply MOCU to this system of ODs?
That's right. That's right. That's right. And that was one of the reasons why we started with Kuramoto model, which gives us a simple but interconnected of ODEs. And the ultimate goal is, you develop the methodology based on this model, however, apply to more realistic systems like the pathway model. For example, we may think about, modifying the drug design, and then thinking about evaluating the efficacy of a designed drug based on a cancer pathway model, based on how it changes the trajectories of cancer, right? So in such a case, many cancer pathway models are simulated based on stochastic differential equations or deterministic ODE. And of course, sometimes they also do Gillespie algorithms or things like that. But anyway, so there is always uncertainty about the pathway model itself. So we may want to think about, how to make all robust decisions despite the uncertainty. And if we can perform biological experiments to reduce uncertainty, where should we focus on?